Ladies and gentlemen, welcome to Math 1451, Calculus 1 with applications. So this will be the first video from the second chapter. So from chapter number 2, which will concern limits and continuity. Well, in this series in this chapter, in the second chapter, there will be 4 series of videos. So the first video will be about the limit of a function. We will be talking about it will be about the introduction to limits. Then we'll talk about operations with limits, how to compute limits, and the third part will be about continuity. And the last part will be about exponentials and logarithms. So we will start today with, basically, I think this lecture will be shorter than the other ones that will follow afterwards. We will talk about a limit of function, what is the limit of function, and we will see a bunch of examples as well. So I will start with basically with the definition. In fact, I'll give you the intuition of what a limit of a function is. Okay, so this is the new chapter, limits and continuity. Well, the limit is a mathematical tool right? For studying the tendency of a function as its independent variable right, approaches some value. That's basically what a limit is all about. It's more intuitive. And let me start with, in this lecture, let me talk about the limit of a function. So the mathematical object that we would like to study the limit of will be a function all right. Now, I think I'm going to start with the notation first. I want you to see exactly what do I mean by that. And the notation will be nothing else. I'm going to write it in color. It will be the limit as x approaches, let's say, this number c, right, of f of x, and this will give us a number L. So this will be read as, so you guys will read this as the following. The limit of f of x, of my function f of x, that f of x is a function, as you have seen in the previous chapter, as x approaches c is L. This is how we read this. So the limit as x approaches z, x approaches c, of f of x will be L. Well, let me explain what is the meaning of these. So these means that the functional values f of x can be arbitrarily close to a unique number, L, by choosing x sufficiently close to C. That's exactly the meaning. But pay attention, close to C, I want to stress this out. So x sufficiently close to C, but not equal to C. Okay, let me say this here, but not equal to C. Okay, right? Well, sometimes we will find convenient to represent the limit statement. So to find convenient to represent this limit, the limit as x approaches C of f of x equals L, by writing, let's say f of x, we can write it in this way, approaches L, so or goes to L as x approaches C. Or sometimes I will even use this notation. Is the same thing as sometimes I will use this notation, L, and I'll put here on the arrow x goes to C, so that is the same thing as all right, so this is the definition. Well, the definition, this is how we're gonna operate in this chapter and throughout the semester. And we will see some functions. We will compute the limits of functions of various functions, like polynomial functions, like rational functions, like exponential functions, logarithmic functions, you name it. Okay, now let's see an example. And let me consider the following function. F of x is x minus 2 over x minus 2. And as you can see, I have to, well, I'm not going to write anything. And let's look at it. You see, this is a rational function. And if you look at the numerator and the denominator, basically they're the same thing, right? They're equal. Well, so let's note that the quantities on the numerator and on the denominator are the same, right? So we might think this will be just one, right? Why not? But the question I want to address is the following. What happens at x equals 2? That is the big question. So at x equals 2, we might run into problems. As you can see, well, if you look at f of 2, This will be nothing else than 2 minus 2 over 2 minus 2, which will give us 0 over 0. But this guy is undefined. Well, therefore we can say that f of x is nothing else than just 1, as x is different than 2. We can just simplify the expression, and that's it. Now the question is, we would like to understand this function. How do we graph? So this is the question 1. Question 2, how do we graph f of x? All right, let's draw something here. I'm going to have the following picture. And so this is 1 here. Here I have a point, and it will go all the way. So this is 2. And as you can see, well, there are undefined points on a graph of a function, right? So now to find the limit, of f of x as x approaches 2. And I would like you to note that that f of x, my function f of x, is going to be equal 1, but not exactly 1. Well, we would like to, so it's getting closer and closer and closer to 1. So with the notion of limits, we will write that lim as x approaches 2 of f of x will be 1. Or if you want, f of x will approach 1 as x approaches 2. Either way, it doesn't matter the notation, whatever you want to use. All right. And now I would like to give you even more intuition about this limit. And let me draw the following, the table. And I would like to plug in some values for x, and then you will see what happens to f of x. Let's say we plug in 1.95 here. Doesn't matter, f of x will still be 1. Let's say we plug in 1.995. Well, still there. Let's say we plug in 1.999. No problem. Still 1. Well, at 2, we have problems. It's undefined, right? Let's say we plug in 2.001. 2.001, again, it's 1. And we can keep going like this. Let's say we plug in 2.1 to be again 1. All right, so well, if you look at this, right, the numbers, we can say that the numbers on the bottom, on the bottom row of the table, of the above table, suggest that f of x approaches 1 as x approaches 2. Well, it's quite clear, right? This is what it suggests. Okay, I think you got some idea from this first example, which basically it's f of x equals 1. Now let's see another example. And now this example will be a little bit more complicated. Well, let me consider the following function. F of x will be equal to x squared plus x minus 2 over x plus 2. And we want to find the limit as x approaches -2 this time of f of x. So that's what we want to find. Right? Well, how do we proceed? First thing, what you need to do is the following. So first off, just plug in x equals -2 into the function. To see what happens. That is a first concern. Always, when we deal with limits of functions from now on, you're asked to find the limit as x approaches something, then you evaluate that function at that point, something, to see what happens. And you will see what happens, and I'm just gonna show you. So let's say f of -2 will be, well, if you look at it, let's -2 squared plus -2 minus 2 over -2 plus 2. And guess what? This will give us, this will be 4 minus 4, which will be 0 over 0. It's undefined. Wow. So maybe there is another way to find the limit. Maybe there is another way to find the limit. Of f of x as x approaches -2. But what is that other way to find this limit? That is the question. Well, we have to look at the function, and when I look at the function, what is my problem with this function? It's a rational function. Well, it looks nice, you know, being a rational function. It has a numerator, it has denominator, and so on. So it's basically the quotient of two functions, two polynomials. But maybe there is something I can do here. Well, and what I mean by that is there a way for me to maybe simplify this fraction a little bit? That is the question. So can we simplify? That is a question I want to answer. Let's look at the function again. Let's write it. Keep in mind that f of x is x squared plus x minus 2 over x plus 2. And the thing is the following. Well, you will, maybe I could write the numerator in terms of the denominator. Maybe I can do that. Well, guess what? I can do it. I can write this as x plus 2 times x minus 1. Surprisingly, I can factor this. And this will be nothing else. These two will cancel. Nothing else than just x minus 1. So that rational function will which looked a little bit complicated at first. Well, not that it's complicated, but it looks simpler. Is this guy. Nothing else than just this guy. Okay. Well, what is the limit then? And we wanted to find the limit as x approaches -2 of f of x. Well, it's quite simple. We have that the limit as x approaches -2 of f of x. I'm just going to replace f of x by my function, which is at this point I simplified it, so it's x minus 1. So this is the lim as x approaches -2 of x minus 1, which will be, now I'm just going to plug in x equals -2, so this will be -2, -1, which is -3. So that is my limit. Once again, the limit as x approaches -2 of f of x will be -3. Now, how do we graph this function? So the question is, how do we graph this function? That is the question. Okay, let's do it. And so this has to go through -1 and 1. So it's going to be something like this. Oops. Oh. Right? This is my function. And this is f of x equals x minus 1. So it's a line, right? According to the graph, as x approaches -2, which will be something here, then you'll go have -3. So it's quite clear. All right. So this is what happens with rational functions if we are lucky and we can simplify them. But let's try also the numerical method as well. Let's draw the following chart. X and f of x. And now let's put some values here around -2, -2.1, -2.05, -2, then -1.999, then -1.95, and let's put another one just for the sake of -1.9. So as you can see, all these values are close to -2. And guess what? We'll get here -3.1. You'll get -3.05. You'll have -3.001. Sorry, no, that was anyway. That -2 is undefined. Well, wait. Yes, undefined. At -1.999 will be -2.999. -1.95 will be -2.95, and this will be -2.9. So as you can see in the table, it's quite clear that we have that f of x approaches -3 as x approaches -2. All right, now let's see another example, and now I'm going to define even a more complicated function. I'm going to define a piecewise function. So example 3. So in this lecture, I'm just going to play with some examples, and I want you to see how the limit works of certain functions. And I'm going to define the following piecewise function, g of x, and now the first piece will be x minus 3 if x is different than 4, and 2 if x equals 4. And now the question is, find the limit as x approaches 4 of g of x. What is the limit of this? Okay, I want you to look at it. And let's analyze it. First of all, what is g of 4? So, well, it's obviously g evaluated at 4. Let's look at our function. As you can see, you find it here. Look at it. So you have this value here, but x equals 4, and then you'll have 2. So g of 4 is nothing else than just 2. All right, so I know exactly what happens with the function at the value x equals 4. Great. But now the question that we want to answer is, what happens when x approaches 4? That is the question. Is that approaches, that is the word. Let's draw a picture. It's very good to see what happens. So we'll have here, so my function will be, so -3, okay? So it will be like this. Here we'll have -3. You'll have 3, and it will go, we'll have a line that will go through these 2 points, okay? And then I have here 2, and here a 2, a 2 and 4, sorry about, so g of 4, okay, 4 is here, and at this point here, I'll have this point, right? G of 4. Well, the point will be of coordinates 4 and 2. Well, look at the picture. This is what happens when you look at it. And I think you can get a pretty clear idea of. And now. Let's make the following observation. Ouch. Okay. Let's point out the following remark. If we look at the graph, when we follow along the graph of g of x, as x gets closer to 4, the graph of g of x, so this is g of x, gets closer to 1, right? So let's write this. When we follow along the graph of g of x approach the graph of g of x along the graph of g of x approaches 1 as x gets closer to 4. Okay, even though that's not where the function is. So in other words, we can say that the limit as x approaches 4 of g of x is 1, right? We can say that. Now let's do the chart. So like I said, this is not quite what I'm doing here in this first lecture. I want you to get I want to build up some intuition of what a limit is. You will see in the second lecture that I will show you methods of computing the limits of functions. Okay, so let's put in some values. Let's say 3.9. Let's see what else. 3.95. Then 3.999. Then we'll put 4. Then we'll put 4.001. Then we'll put 4.1. And then let's do another one. 4.15. All right. This will be 0.9. This will be 0.95. This will be 0.9999. This will be 2. This will be 1.001. This will be 1.1. This will be 1.15. Right. As you can see, that's exactly what happens. Even if you look at the chart, well, even though if you look at the chart, be aware that this chart this method can introduce some errors, but it will give you an idea of what the value of the limit is. As you can see, if I plug in all these values closer to 4, I will obtain a value closer to 1. As you can see, around 1. Everything happens around 1. So that's why this is not quite a method. This is just a way for you to see what will be the value of that limit. It is not a proof. You will see that we'll develop more effective algebraic methods to compute the limits, but that will follow in the second lecture. Okay. Now, let me just, well, you have seen 3 examples. Let me just talk about one-sided limits. And when I talk about one-sided limits, you will see that I'm talking about limits from the left and limits from the right. And the first one, let's see a right-handed limit. Let's call them in this way. Right-handed limit. We want to see what this is all about, right? Okay, so the notation will be the following. We write lim as x approaches, and I'm gonna write it in red so that you can see that I distinguish between x goes to c plus of f of x equals L. And when I look at this guy here, this guy here means nothing else than just x approaches c, but like I said, it approaches c from the right. So I'll This is what it means. It approaches C, but from the right. It will approach C from all the values which are greater than C. So we write that the lim as x approaches C plus of f of x equals L if we can if we can make, let's say, the number f of x as close to L, right? As we choose x to be sufficiently close to C on the interval, and I'll draw a picture so that things will be as clear as possible. On the interval, it'll be C, B, right? Immediately, to the right of C, that is to the right of C. This is important. That's what I mean. Okay, now let's draw a picture so that things will be clear. I'll explain immediately what I just wrote by just drawing a picture. Okay, here we go. So I'm going to have the interval here. Let's say I have C and B. This is open interval, right? And keep in mind that I'll have here a number x, which will go like this. So this is x approaches C plus, right? It comes from the right. That's what I mean. We'll approach C from the right. Okay, well, guess what? Similarly, since we can define the left-handed limit, okay? And again, we write, this time will be lim as x approaches C minus, and when I mean C minus, I mean from the left, right? The previous one was coming from the left, from the right, and now it come from the left. But both of them are approaching the same thing, but coming from different directions. It's like, well, I wouldn't say this example is a fortunate example. It's like two trains colliding at some point. Both of them are approaching that point of collision. Anyway, this is just an unfortunate example, but it's an example. So as you can see here, this will be nothing else than just all these values that will approach C, but with x less than C. That's what it means, right? So we're going to write this as lim as x approaches C from the left of f of x equals L if we can make the number well, if you want to say it like this, f of x as close to L as by choosing x to be sufficiently close to C, and this is important, on an interval, let's say an open interval AC, to the left of C. This is important. Okay? See. And I will draw a picture. No, I'll say here immediately. Maybe I should keep this word immediately. To the left of C. So this is important. And again here as well. Right? Okay. So now let's draw the picture. And we'll explain immediately. So similar, this time I'll have this interval A, C, and now guess what happens? I have all these values, they're approaching from they're coming from the left. From the left, right? Okay. So this is basically how we deal with one-sided, one-handed limit, one-sided limits, left-handed and right-handed. Now let's see some examples. Example 1. Let's define the following function. Let's take h of x. So I'm going to take a piecewise function. 1 if x is less or equal than 3, and -1 if x is greater than 3. Now the question is, what is the limit as x approaches 3 of h of x? That is the question. And we would like to see, because this is a little bit, I wouldn't say delicate, but let's see, let's draw a picture so that we can get some intuition over this. So this is, so here I have 1, 2, 3, and 4. Now let's see, so 3, so I have -1. All right, and here I have, let's say 1. So here I will draw this at 3, oh. Right? And also, I know that for x greater than 3, so I will not include this, is -1, and it goes like this. So this will go like this, this will go like this. Well, it's quite clear from the graph that the lim as x approaches 3 from the left of h of x is 1. It's quite clear. And now the limit as x approaches 3 from the right of h of x will be -1. As you can see, the limits are different. This the one side, the limits are different. The right-hand side is not the same as the left-hand side limit. But now we need something more. And the main ingredient, in fact, which is not yet in the picture, is the following, and this is theorem. We need this following theorem, which says that the two sided limits let me see. So the two-sided limits or maybe I should say, okay, the limit directly. X approaches C, and pay attention, I'm not saying from the left or from the right, and f of X exists, and this is a big word here, exists, because it's not guaranteed that all limits exist, and we'll see examples. So this exists if and only if, right, the two one-sided limits and when I say this, I'm talking about the limit as X approaches C from the left of f of X and the limit as X approaches C from the right of f of X. When both of these limits exist and moreover, and they're equal. Well, this is important. Exists and they're equal. These are the two words that, well, now you have an idea from the previous example if the limit of, what is the limit of as X approaches 3 of h of X? Well, unfortunately, the left-hand limit, which is lim as X approaches 3 from the left of h of X is 1, but and also the limit as X approaches 3 to the right of h of X is -1. So the two values, and 1 and -1, do not agree. So there you go. You got the answer. The limit doesn't quite exist. All right, let's see some other examples. So example number 2. Ouch. I'm going to say this. Well, let's say we have a function for which the limit as X approaches 2 from the left of f of X is 1, and the limit as X approaches 2 from the right of f of X is 1. Well, guess what? The two values agree. So this means that both of these limits exist, and in other words, there exists lim as X approaches 2 of f of X. And moreover, this is just 1. So both left-hand side, left-handed limit and right-handed limit exist. They agree, they have the same value. So this implies that the limit of the function at x equals as x approaches 2 is 1. All right, according to the theorem above. Example 3. Let's say we have lim as x approaches -2 from the left is of f of x is -3. And we also know that this is the same as x approaches -2 from the right of f of x. Well, again, by the theorem, you can conclude that, and again, this follows from the theorem, that there exists the lim as x approaches -2 of f of x, and this will be -3. Very simple, right? Okay. And let's see some other examples, and I think we'll stop here. I think this is basically what you need as an introduction about the limits of functions. Let's see example 4. Well, what if we have something like this? We have the limit as x approaches -3, 3 from the left of h of x, let's say, is 1, and the lim as x approaches 3 from the right of h of x equals -1, as we have seen. Well, we can say the following: both one-sided limits exist, right? But they are not equal. In other words, this implies that that the limit as x approaches 3 of h of x does not exist, right? The two left-handed limit, so the limit from the left and the limit from the right do not agree. So as we have seen also here in this example, look at it, that's exactly the same thing, right? Okay, I think this is this sums up the first lecture. As you have seen, this was more like an introduction. It wasn't like going too much into details. I just wanted to show you how basically the intuition behind the limit of a function. In the next lecture, which will follow sometime this week, we will see methods of computing limits of functions. All right, I think this is a good place for me to stop. Thank you very much.